It has a story that many of us heard when we were young, and it has been told and retold so many times that it has become one of the most famous anecdotes in the history of science. The story of how Isaac Newton discovered gravity from a falling apple. The year before, due to the outbreak of the plague, most of Cambridge's scholars had fled the city. Among them was a young man named Isaac Newton, who at the time was just 23 years old. Newton, like many others, believed that the Earth was an infinite distance away from the sun. A small apple falling from a tree experiences the same gravitational force as the moon orbiting the Earth. One of the key features of calculus is the use of derivatives and integrals to analyze rates of change and accumulation. His laws of motion and universal gravitation, along with his contributions to calculus, revolutionized our understanding of the natural world and laid the foundation for modern physics and astronomy. His work laid the groundwork for classical mechanics, a fundamental pillar of physics that describes the motion of objects on Earth and in outer space. This framework enabled scientists to predict and understand the behavior of celestial bodies with unprecedented accuracy. Furthermore, Newton's contributions to optics advanced our understanding of light and its properties, laying the foundation for modern optical technologies. Before Newton, the scientific community lacked a comprehensive theory to explain the motion of celestial bodies. In essence, Newton's story serves as a timeless testament to the power of human curiosity and the transformative impact a single moment of inspiration can have on our understanding of the universe. So the next time you see an apple falling from a tree, remember the profound implications that such a simple observation can have on shaping our world. With his discovery of gravity, everything changed. Newton showed that the same force that pulled an apple to the ground also kept the moon in orbit and the planets in their path around the sun. This realization led to a paradigm shift in the scientific community, establishing heliocentrism as the accepted model of the solar system. These concepts allowed scientists to study the motion of objects in greater detail, leading to a deeper understanding of the physical world. Newton applied calculus to a wide range of phenomena, including the motion of planets and the behavior of light. His work laid the foundation for classical mechanics, which describes the motion of objects on Earth and in outer space, and for optics, the study of light and other electromagnetic radiation. But as Newton pondered further, he recognized that, while the force of gravity is the same for all objects, the acceleration caused by this force is different. It depends on the object's mass. The acceleration of an object due to gravity is inversely proportional to its mass. This means that an apple, with its relatively large mass, will accelerate downward at a rate of approximately 9.8 meters per second squared, whereas a bowling ball, with its much smaller mass, will accelerate at the same rate. He was also aware of a recent discovery made by a Danish astronomer named Ulraimer, who had calculated the distance between the Earth and the Moon by measuring the slight variations in the orbital period of Jupiter's moon Europa, which changed depending on whether the Earth was moving towards or away from Jupiter. Raymer had calculated the speed of light, and although he didn't know the exact figure, he estimated it to be around 800 times the speed of sound. But the story doesn't end there. That one moment of inspiration led to centuries of scientific discovery, changing our understanding of the universe forever. In his mind, he questioned why the apple fell straight down and not sideways or upwards. If the force that makes the apple fall is the same force that pulls it down, then surely the Earth must have an effect on the motion of other objects as well. Could the same force keep the moon in orbit around the Earth? And if so, could that same force keep the Earth in orbit around the sun? We open on a tranquil afternoon in the year 1665. The location is a serene garden, not too far from the town of Cambridge. Now back to Newton, in his garden. As he sat quietly, thinking about these recent discoveries, he noticed an apple fall from a tree. Let's rewind a few moments. Just a couple of decades earlier, the most widely accepted theory for how the planets move was heliocentrism. This theory, proposed by Copernicus, placed the sun at the center of the universe, with the planets revolving around it. However, without any real mathematical explanation for how objects stay in orbit, the theory remained incomplete. Now, enter Newton with his newly conceived idea. What if all objects are attracted to each other? The strength of this attraction depends on the mass of the objects and the distance between them. If this were true, then the force of attraction between the Earth and the Moon would keep the Moon in orbit around the Earth. The same would be true for the Earth and the Sun. With this, Newton had discovered one of the fundamental laws of the universe, the law of universal gravitation. He realized that the force of gravity was the same for all objects regardless of their mass. After making this groundbreaking discovery, Newton went on to develop calculus, which provided the necessary mathematical tools to describe the behavior of objects in motion. The impact of Newton's work was monumental, but Newton's influence extended beyond the realm of astronomy. Today, his legacy continues to inspire and guide scientists and researchers across various disciplines.